Well, hello, and welcome back to Old School Coding, where we are working on a simulation for a microcomputer that might have existed in the late 80s, early 90s, written in the C99 programming language, which is substantially similar to what I worked with back in the late 80s and early 90s, using the software engineering techniques that, again, were in common use in that time period between me and my cohort of friends and co-workers at the time. So this is an exciting time right now. We now have our CPU chip mostly done. We don't have interrupts yet. That's okay. We don't have DMA yet. That's okay. We have the clock controller. We have the system controller chip. We have a way of doing RAM and a way of doing ROM. We have a memory decoder that includes a shadow facility. And now, as you can see on the screen, we have what may be a viable boot ROM. So I sat and tinkered around with this. I had forgotten what a joy it was to write 8080 machine code. No lie. I actually have a great deal of joy on this one. And you'll notice that we have our TCP TTY sitting there in a window, just waiting for us to connect to it. Yay! We've already tested all of those little bits. So now what we want to do is we want to actually construct a computer system, simulate a computer system that matches this. And I am changing some of my plans. I've decided that I only need 2 kilobytes of ROM. In reality, I probably only need like 32 bytes of ROM if I'm really honest. But for now, I'm going to do a 2 kilobyte ROM, and we're going to put a ROM monitor in it. Long term, the only thing the boot prom does is yoinks in your boot sector from your boot disk and starts it going. And you might have a boot disk for CPM and a boot disk for Forth and so on. That's my plans long term. Short term, however, I do want to have a boot ROM that has some kind of ROM monitor in it. And we'll see what I've got as I put it together. But let's start with actually building the actual system up that's going to run this. Now I could turn off the TTY from the screens. We won't be actually talking to it at any time really soon. You see I've got my basic system definition written up here in this assembly code file. And I'm saying that I want 62 kilobytes of RAM and 2 kilobytes of ROM. I want to have a CDEV controller, well, several CDEV controllers sitting there for TTY, CRT, paper tape, and line printer. So I'll have a high-speed paper tape reader reserved. I won't actually have it implemented yet because it's not really a CRT. It's not really a CDEV controller per se, but we'll reserve those ports. They won't be added. And then we have the BDEV, which we've already tested. Our test version of the BDEV provides us with scratch disks. We will use something like that. And what we will need to do in the system simulation is provide a way to load disk images in, and then a way to say, well, when somebody writes to the disk image, I want it to update the file. And I think the best way to handle that is to use mmap. We'll see about that. Anyway, but the first step is to start building the system. So Inc. And here's all of our header files for all of the things we are building. And I want to start off with a VoidStar 8080.h. And we're going to build this up. This is going to look just like a simulation module, but it's going to own instances of everything else. So we can take a look at, say, i8080, which also has a whole bunch of complexity in it. And I can kind of pattern myself after it. So type def struct VoidStar 8080, like that. And this is actually going to be S VoidStar and P VoidStar, and because as long as I'm simulating, I may want to simulate multiple of these in parallel. I may want to have 8 of these machines spread across my desk talking via a network port someday. So we're not going to use any ideas that say there's only one. Now, the one thing that we are constrained about is our system clock, our simulation clock, which is stepping in sync across all of these guys. That's just because clock is itself a singleton. Resolving that will be a trick. But anyway, it does mean that we'll be executing all of our systems in parallel. Now we'll do, obviously, all the work on one system at a time for each clock edge. But yeah, we could go multiprocessor on this. Neat, huh? There will be a trick on how we have things set up to, if we have any devices that are shared. But yeah, so no singletons here. C-stir name. So our system is going to have a name. So init and invar and linked are my standard entry points. I'm not sure I'm going to have BIST, post, and bench. Really. I think this is just going to be something where I'm going to code it up and run it. What does it mean to do a built-in self-test of the entire system? Is that meaningful, given that we've BISTed each of the individual components? We will add that. If I figure out a test I want to do, I'll add it. But for now, I'm going to leave it blank. So what are our components here? Well, obviously, I am going to need to do most of the things that I already do for the 8080 test, because it builds up a mostly working system. So it does a CPU test sys. So we can just grab this. So we need a CPU, we need a clock generator, we need the control stuff, we need a decoder. We do not want a test dev. Now, ROM chips, I only have one ROM chip. I have 4 RAM boards. Now, this means that I'm going to do something that I have seen in systems at the time, which is we had a RAM board that was 16K, taking up the last 16K, but we also had a ROM taking up the last 2K. So in that instance, what we're going to do is we're actually going to waste 2 kilobytes of RAM, which will never be visible because the ROM is going to be there. Now, maybe there will be something we can do in our VoidStar that says, rather than the normal shadow, so shadow takes our ROM and maps it in at 0, and then it snaps back out what it's referenced its normal address. Perhaps we'll have a thing in the future that says, okay, we can get rid of the ROM and expose the RAM that was behind it. Kind of cool. So because we're a system, we control the reset input and the ready input. Those are all owned by the system. Here. We don't need an SS. So what else do we need here? Well, we need a block device and character devices. So cdev. We have cdevs for TTY and CRT and LPT. And I am not going to hook up paper tape yet, okay? Because paper tape, we don't want paper tape coming out on the window. I will need to hook up something so that when you start reading from the paper tape, it will feed it from a file. When you write to paper tape, it has to write it to a file. That's a different kind of a device, and we don't need it yet. Paper tape was mainly in use before disk drives, before rotating media was something you would have all the time on a microcomputer. So for instance, you might have your basic interpreter might be on paper tape, and you would hook up the paper tape to the paper tape reader, and it would read it in and write it into memory, and then you'd be using BASIC. Alternately, if you had a disk controller which you added on to a computer system, the paper tape that you feed into it might be the special boot program that boots from the paper tape, or boots from the disk. This is useful if it's more than a few instructions. You know, if you're on an MSI or an Altair, you might, key in 4 or 5 instruction, bootloader if you can do that. But if it's a rather longer thing, you'd want that on paper tape. And the paper tape may simply be a paper tape reader attached to a teletype, where when you start the tape going, it just simply streams it in as if you were typing it. Okay? So we're not going to do that quite yet. And we need a BDEV, which is going to be our disk controller. Just call that BDEV. So BDEV is our thingy that will support all of this stuff. And BDEV itself has all of the signals, and it's going to want a seek function, which we'll have to provide. And in our case, the seek function that we're going to provide to BDEV may actually need to have access to VoidStar 8080. We'll see when we start to do the implementation. So this is not going to compile yet because it's got all of these things that it's going to do. But let's go into source. Okay, so now if we force a recompile of the system, it will pick up the new file, and it says, oh, you forgot to include a whole bunch of things. And that would be I-8080 and I-8224 and I-8228, decoder, CDEV, BDEV, ROM 8316, RAM 8107, X8, X4. Get all those, and now we see that the definition has no type or storage class. Because I mistyped some punctuation. So, there we go. We have now defined the public-facing view of what one of these things looks like. Now, I'm going to want to actually start this VoidStar 8080 from the main. So I'm going to start with I'm going to have a new thing here. And in fact, what I want to do is always use the capitalization. Like that. So what will happen is we are going to start the simulation. We're going to say, please run VoidStar 8080 main. Let's get in here. So kind of like we run BIST and we run bench, and we run our CDEV test, I'm going to say, just here, if the parameter I put in, if I type if, oh, come on. Okay, and that will turn control over to our function. Now this says we have an implicit declaration of the main function because I put it in the wrong file. It needs to go in there. Now I need these in both of them. The other file is actually going to get the implementation of it. But for now, there we go. No BIST coverage. It's an extern int. Okay. So this is going to play hob with anybody that expects the name of something to be an identifier, isn't it? So in theory, if I get called here, this is passing along any additional arguments. So I would be able to look at argv sub 0 through n and pick up the parameters that I would pass. So I'd say, here I might say report.sh, amper, semicolon, and then bin live coding VoidStar 8080. So we are now actually executing this stuff. So we're getting into an it. We are going to, from linked, we are going to say void star 80 underscore in var of sys. We know we're getting there, so we can delete these. There we go. So what do we need to do here? Well, we need obviously to initialize our stuff. So, yeah, having a weird name like that could cause problems. So just doing it. So the weirdness happens if you write things back in the wrong order, and then you grab the logs before it recompiled again. You know how it goes. So what happened there was I wrote the .c file, it triggered the build. Then I wrote the .h file, and the .h file got written before we got around to the thing that starts waiting for things to change. So init needs to finish initialization. So we do i8080 init of sys. Oh. Just like that. So gen ctl dec tty crt lpt and bdev wishing I had appropriate constructors. Okay, so this is 8224. Implicit declaration needs to be lowercase because I'm a Goomba. There we go. So what else do we want to statically initialize here? Well, we need to do the ROM chips. It is possible that we may want to instantiate VoidStars with varying numbers of ROMs and RAMs. I don't think that's going to happen anytime soon, so we're not going to wire it into what we've got here. So now we do a ROM 8316 init of sys arrow ROM of chip. So I'm going to call it ROM1 through ROM-N. And RAM1 through RAM-N. This needs to be RAM 8107X8X4. Nope, 8107. I had it right. So that initializes those. Oh, and we need to initialize those two edges. And we don't actually have edge. Oh, edge in it, too few arguments, right. So at power up, reset in is going to start low, and ready in is going to start low. So power on reset for our systems always starts with reset and ready low, and we're going to bring reset high and ready high manually. This maps into the way you would start an 8080 from a front panel if the system didn't do a whole bunch of stuff for you, which is literally you hold down those two, bring the power up, release the reset, and then release ready. Now, in our system, because everybody is talking to the same ready pin, whoever set it last wins, because we are not doing tracking of, I set it and I'm holding it. I'm setting it and I'm leaving it. So it's all fire and forget. If I want to have multiple sources of ready, where CPU sees ready only when all of the sources of ready are saying they're ready, we would have to have some code, possibly in a new module, which would do that. Now, it could very well be that the only place we do that is here, the idea being that only the addressed device would know, but we might have a switch. So we now have two sources of ready. We have the switch on the front panel, which might force unready, and then we have the device. We also have the possibility of, if you make a memory access which doesn't go to a device, maybe ready never comes high. So, thing to bear in mind. So we've done that. So the invars, we don't call yet. No, now it is time to do the invars. Bink. Like that. Now we did some stuff with the CPU, which I kind of liked, that we grabbed all of the fields. Inc. i8080. Was it the CPU? No, it was BDEV, wasn't it? Yes, this BDEV all thing. All of these are of different data types, so this doesn't work very well for us, so I am going to not do it. However, all the stuff that we init, we're going to go down here and call the invariants. Like that. So bdev invar was not declared. We don't have any bdev invars. We should. I forgot to do a bdev invar. Okay, so now it should be, we have the function, but I forgot to declare it in the header. So source. I'm going to peek at it in the far upper left here really quick. Let's see. Name, reset, disk, track, sector, data read, data write, invar of data. Check that seek is there, cursor and cursor limit, whether equal or not, we don't care. That's good. So up the top, we're now going to say VoidStar 8080 linked sys. And actually, it's up to the init function for VoidStar 8080 to link together everything it owns. So yeah, because linked says we linked up everything that comes from outside VoidStar 8080. We have nothing yet. So, okay, that works. If somebody is going to instantiate multiple systems and there are links between them, then we do need to have this out here. Or is this a special case because we are standalone? I think this is a special case because we're standalone. There's my reasoning. Because we're standalone, we're going to do our linking, and externally we can call linked. We could say, we have linked you. Please check, and that will provide. So in a multiple system, we would do that. That means the invars are going to get called twice, but that's perfectly okay. So potentially, if we are hooking up multiple VoidStar 8080s in some sort of networking configuration or shared device configuration or even shared memory configuration, it is quite possible that doing so would violate our invariance. At this point, unused, semicolon. And now we're going to start getting crashes because we're not really there. And I'm going to take a quick break. And I will be back to continue this later. I'll call that one 31B because this is a very short introduction to what is going on with this guy. I may get the jump on some of the just knitting this together off stream. I will talk to you then. So meanwhile, as I always say, keep it small, keep it fast.